All right. Hello, everybody. Let me just check some settings here. Probably edit this out when the audio comes through. Okay, so welcome to Gears of Resistance. We are on our third episode, and I've been very delinquent in getting this out, and I apologize. Life happens. So last time we talked about voltage, we talked about current, we talked about resistance. I think I was supposed to promise something on capacitance and inductance, or capacitors and inductors, and what they are and what they do. So tonight, that's what we're going to try to hit. But first, just wanted to kind of make this more than just because it's going to be a podcast, more than just a video, how-to. There's plenty of just great how-to videos if you want to know. But the idea of this podcast and this video is to kind of share just what I'm working on, tinkering, the process, how it works, especially for those who are professional amateurs or amateur professionals like myself when it comes to it. We have day jobs, and then this kind of electronics embedded design is kind of we do work on the side. We take up contracts and we do kind of consulting work, but it's not our full-time gig, if that makes any sense. So with that, I wanted to kind of share some things that I've been working on. And I think to do that successfully, I hate technology sometimes. Let's see here. Did I make it too small? I think I made it too small. We're going to share our screen. So anyway, the first thing talking about is a new app that literally just came to my knowledge this evening, and I have been playing around with it. It's called Embryo, Embrio.io is their website. So it's Embryo website, again, Embrio.io. And what it is a quote-unquote, on the website, a visual real-time development tool for Arduino programming. It looks to me like a lot like LabVIEW. It also looks kind of like, Scratch on steroids, if you're kind of used to that kind of software programming, if you're just into, learning and teaching yourself or teaching your kids. But LabVIEW for people probably have a little bit more professional use, but not quite. Maybe, you may be a researcher who does, environmental stuff, but you're not necessarily an embedded developer, embedded engineer. Things like LabVIEW and some other pieces of software make programming easier. They kind of make it, they simplify, they abstract away the complexity of actually bit banging or actually just typing out lines of code with kind of plug and play Lego blocks. There is a whole religion behind whether or not this is a good thing or a bad thing. And certainly there are applications, especially in the embedded world, where it's probably not ideal because you really want to have a deterministic, you really want to understand what's going on at any time with your hardware and the firmware that's running on it. With that said, a lot of us aren't designing the circuitry for the replacement for the space shuttle. We aren't doing potentially even just things like medical devices. Some of us are just doing, super hobbyist kind of work, where having that level of deterministic understanding of what exactly is happening is probably too much. And that's where things like Embryo, in my opinion, and I'll go on the record saying that I'm very much anti professional priesthoods. I think all too often, those of us in a profession, and for the record, it's kind of like me speaking at both sides of my mouth. So on the one hand, I have my professional engineering license, so I've done, I've gone to school, I've done the work to take the test. So yes, I have the in this case, the state of Maryland's professional board has said, yay, verily, you can practice professional engineering in the state. Which on one hand, you would think, okay, I've put forth, this is almost 20 years of effort. I want to protect myself, and there is certainly good intention of protecting the public. That is a very valid reason to have professional licensing of all things. Doctors, lawyers, engineers. And I appreciate that because I be one. But there's a lot of applications where it's not needed, and I think knowing the difference is very key. And I think as a profession, and this is going the rant I did not want to go down, we need to be open-minded. And here's my example. Here's how I rationalize why I like things like Embryo. And I'll get to the actual uses here in a second. But why I like it is sometimes, again, depending on the application, and there's a lot of applications that I do, probably most of them. I'm working on deadlines, very tight deadlines. I'm turning around prototypes, and the less I have to start from scratch, the more productive I am. It's the whole reason why I use open hardware, open source hardware, and buy components. I'm not soldering together my Atmel and making my own, power, power supply circuit. I'm grabbing an Arduino or a Raspberry Pi and going from there because it saves me time. And I think Embryo is the same concept on the software side. And embedded software, if you're a software engineer professionally, there's lots of tools out there, lots of tools, debugging tools. And I'm talking, things up the stack, not the, when you're writing web apps and you're writing Windows applications, lots of tools. Embedded design, and I'll be honest, it doesn't lend itself because of the complexity, the fact that you're dealing so close to raw metal, or is it just lack of imagination from us, embedded folks, where we haven't designed tools that make us more efficient on the firmware software side? I think this, from what I've seen, and what I like about it is, and I'm talking Embryo here, you hook up, it works obviously with Arduino. You can see in real time as you're linking these blocks together and getting and you hook up your hardware, you can see in real time, graphically as well as text-based, how things are changing. So if you hook up, like they use one of these tutorials here, let me see here. There's a lot of great videos actually, and I literally just started looking at it tonight. But oh, this is more stuff I haven't even seen yet. Let me go back to the basic projects. So here we go. Beginner projects is what I was looking at. Let me scroll on down to the distance sensor thing I was looking at. Where's the hobby servo? Yeah. And again, a lot of good YouTube videos. Oh, I thought there was more text, more demos. Here we go. So as you're hooking up say some sort of distance sensor, in this case is an infrared sensor, you can get real-time readings into the code. So you can change, you can see how, say you do a voltage divider circuit, right? And if it's, I put the variable resistor connected to the VCC versus connected to ground, I get a different behavior when I tap in and do the reading on my voltage divider circuit. Here you can see real time, instead of hooking it up, writing some code, pushing it over to the Arduino, pressing the, letting it run and seeing if your logic is either the way you intend it or is it the opposite. You got to go back in the code and say, instead of saying if it's high, I want to say if it's low. Kind of reverse or correct your, am I dealing with positive logic or negative logic, or what's the is the switch being on a high or does it generate a low? So this again is Embryo app. And full disclosure, I wrote the gentleman's name that I talked with was Ezra, and he did give me a sneak peek of the Pro version. So I'm using the Pro version. So thank you, Ezra. I'll throw that out to you. But bottom line, I think he's on the right track. I think firmware is complex, but our tools don't have to be, and our processes don't have to be. I think that we can work to having better tools. And here's the way I liken it to. When I came out of college, everything was still C, C++. And even at the time, we had some folks, professors, lecturers who, again, as a computer engineering major versus comp sci, to really understand the hardware, you have to understand assembly. And that's true to a point. Does that mean, though, that we write all our projects still in assembly? No, we don't. We do some C, we do some, every now and then, if you have to do something that's really critical, yeah, you'll throw in some assembly. But, certainly having the appreciation is very valuable. We don't, again, we don't write in it. I think the same thing will be true for both the hardware and the software of this revolution we're going through with, which is kind of a misnomer. My first micro was a basic stamp 20 years ago. But the point is, the tools have gotten better. The hardware has gotten, now some would say, again, and I understand, you've abstracted too much out, and people don't appreciate what it is they're really doing. And again, I'll go back to my thing as a professional. Yes, there are very much applications where you need it. Medical devices, the space shuttle. But does a water, a cat food dispenser, a watering lawn watering, sensor that measures how dry your grass is and turns on a sprinkler, can those things be done just as good, just as safe, just as but quicker with better tools, such as Embryo, such as Arduino? I think so. And if nothing else, the bottom line is they are gateways to people who really love this stuff, will go further and will take it and learn. But I think eventually, we already seeing these things, especially Arduinos, in commercial viable products. Now, sometimes 2 or 3 iterations down, once they've added a bunch of features, yeah, they switch over to an ARM-based solution, or, excuse me, it's really dry in here. Something a little bit more powerful. But then the flip side, then the people at Arduino are playing the cat and mouse game too. They're always releasing new hardware. In fact, just a couple of days ago, there's 2 new ones. I should probably find a link to that and put those in there. They announced new hardware, and it's more powerful. What I can do with an Arduino Une used to take me 3 or 4 separate boards between the Wi-Fi connectivity, the Bluetooth, or still, yeah, it doesn't have Bluetooth built in, but the Wi-Fi and some of the more computational intensive tasks. It used to take sending data to a computer and spitting it out. Now I can do it all right on the Yun. So I think these things will get more powerful. And I think that, as the hardware gets better, more powerful, I think it's realistic to expect that the firmware development on the software side will get better, that our, the IDE can take lessons from the higher level software development and things like LabVIEW, and not make the trade-offs as drastic as some people seem to want to make it. That, if you use something like Embryo, well, the end of the world will incur. I think this is maturity. This is an evolution. And I think that to think that we are as far along as this stuff will, we've plateaued in the evolution, I think is disingenuous and unfair to the people that design the code and the hardware themselves, that, who are truly masters of this. So they're not only are they building cool projects, but they're building the building blocks. I think we'll get there. And that's my rant, and that's Embryo. So again, embrio.io. Check it out, support them, especially if you are a maker and just starting out. I think it's a really powerful solution. And again, I'm going to give a better review once I've played with it more. But I think the kind of the real-time interfacing with your hardware and getting real-time, playing with the hardware and making changes and seeing how the hardware reacts, I think is really cool, whether you're a novice or a professional. Okay, what else are we dealing with? What other projects? Ooh. Let me share the screen again. That's the wrong one. So we'll talk about it a little bit here. I'll get off the rant and we'll get into the real stuff. But curious if anyone's used this Siglent SDS1052. It's a 50 megahertz scope, digital scope, 7-inch display, has a frequency counter also, and it has I think it's one giga giga samples per second, I think. But so here's my use case. I need a very inexpensive scope, but very not, I don't need a super powerful scope. I'm not going to be dealing in anything approaching 50 megahertz, at least I don't think. Let's say like we're doing projects with some infrared receivers, or looking at pulses of driving a servo, and from an academic perspective too, and being able to be on the road and in the field. So I'm probably going to look at getting one. I just bought one. Another one though for teaching and using as a field scope. So I'm curious if anyone has bought this, used it, and what their thoughts are. They could send me an email. We'll put all that in the show notes. I'd like to talk to somebody with some questions. I got one again because I had a really good gift card from Amazon, so it made purchase price real cheap. And it's one of those things where I needed something very portable, not huge. That was more important than specs. There's one that's, I think, the similar model, 100 megahertz, but it was an extra $67, and again, just wasn't worth it. But I'm curious, has anyone used the Siglent 1052 portable digital oscilloscope, and what your thoughts are? And last but not least, of just the things we've been working on. So I've had the PrintrBot here for a month now, and using it for a lot of projects that need that would benefit greatly from having a very nice custom enclosure. Again, from a prototype kind of concept. But the problem was I was always running out to, especially until I got it fine-tuned, the print, a lot of problems with all 3D printers. Especially as you get bigger prints, taller prints, if it doesn't stick, then you basically start printing in free space. And it's a pain in the butt. So I wanted a system, and I had just got a new Raspberry Pi, so I had my older one now, the original, just sitting around. And so basically found some things on some files on Thingiverse to print a Raspberry Pi camera bed mount. So basically the idea, as you can see here on the video or the screen, is take your Raspberry Pi, take your Pi camera, print out this little enclosure that connects to the bed of your PrintrBot simple metal, plug that at the end, and now you set up some software that streams onto your network, and then you can take an app, and I'm using VLC on my phone and my tablet, and now I can wander around the house and check in with the 3D print to see how it's doing. I also I got the Pi Noir versus just the straight Pi camera, whatever they call it, and a little couple $1 little infrared, like a security camera. I forgot what they call it. Not a seeker, but a illuminator. So now I can shut all the lights down in the room, go out, and track this thing even in the dark. So the Pi Noir is an infrared kind of see in the dark camera. The little illuminator provides just enough IR light that the camera seems to pick it up, and now I can, even in the dark, just check on the print. I don't recommend ever printing something over while you're asleep, but if you have to kind of wander around the house, take care of some other chores, and you want to save some bucks with your lights, this seems like a pretty cool solution. One thing, let me so one issue though with the Raspberry Pi camera is that it is and I'm not a photography guru, so let me think how I want to say this. It doesn't have a wide field of view, or it's very zoomed in. I don't know how you would say that, but so you put this little camera at the very edge, and it's pointing down towards it. It's kind of like you only have this maybe 2-inch by 2-inch part of the plate of the bed of your print bed. So there are these little lenses, and I'll probably put a link again on in the show notes for your smartphone. This one is built for the iPhone. But what you're supposed to do is take it, plug it in on your phone like that, and you get comes with 3 lenses. This is like the wide angle lens. But the same little guy here, you print this and put this over the Raspberry Pi camera, and now you can see the whole print bed, except for maybe half an inch from where that's right underneath it. And that now you can actually see the whole print bed. So the nice thing about actually attaching the camera to the print bed is that now, since it's moving with the printer, your thing that you're looking at, what you're printing, stays stationary. It's whereas if you had the camera off, separate, as the print bed moves back and forth, your camera can't focus on it. So now when it's stationary with the print bed, it moves as one unit. It really works good. I'll put the links to what I printed on Thingiverse. It was from a gentleman named, his username is GoR, so I appreciate that. Didn't have to make any mods to the files that work. It snugged pretty well. So that was cool. And also, again, the little these little $4 or $5 camera lenses really work well. Actually, they even work well on my iPhone. I took some pictures with the phone. I was pretty impressed. One other thing you have to do, and again, I apologize for having to drink but my throat is dry. The Raspberry Pi camera comes with, I think, like a 4-inch ribbon cable to connect between the camera and the Pi. That's when your printer's moving back and forth, and there's a term for how that range, and I can't think of what it is. That's not enough. So I ended up ordering a 2-foot long cable that's on its way from a slow boat to China, because for some reason, I love this is how the world, we'll go on another rant here about the global world economy and logistics. So my daughter the other day tripped on some ice out here and kind of sprained her wrist a little bit. So I had to go down the road just maybe about half a mile to a CVS and get one of those little ace bandages. And so for me to drive, like, again, maybe a mile, a little bit more, and get an ace bandage and bring it back to the house, it was like $6. This cable that I needed is coming from China. It is $3, including shipping. It's coming all the way from Shenzhen. So that, again, just one of those things where it's amazing how on, little stupid dinky ace bandage, $6, that's a mile from my house, versus getting not a complex thing, but still a ribbon cable, which has very fine copper traces, all the way from China to my house, $3. Interesting. So let's move on here real quick. We're going to start talking what we were here for, and that is capacitance and inductance. So just real quick, I don't know how this is going to work with my microphones. Let me bring this in a little bit. Let's see if this is any better. So I don't want to talk into my mic, so you can actually hear what the heck I'm talking about. So real quick summary review. We drew the whole little water tank that has a little spigot on it. We'll give it a little knob here. Oh, that's beautiful. And we said if you fill it up with a little bit of water, that's kind of like low, small voltage. And the more water, well, that's your high voltage or higher voltage. And then, so this is basically the water level kind of represents the battery. My little spigot here kind of represents a resistor. I open up the spigot, I can let more water flow out. More water is my current in amps. That's my resistor and resistance. And my battery, that's the voltage. So that's the actual electrons flowing. That's the spigot's my resistor. and the water level is my voltage. And I need to take a real quick 1 second break here, and I'll edit this out later. Okay. I apologize for that. So let's now add capacitance to the mix, or start off just with the generic capacitors. Capacitors. Okay. God, that glare. I got to get something with that glare. Can I? So anyway, so if you look on your circuit board, you may have these little cylindrical things. Sometimes they're blue. One side, maybe they'll have a little arrow pointing down. They usually have maybe a little cross on top. That's so when the capacitor blows, got a room to go. Sometimes there'll be little ceramic discs. They just kind of look, and this is kind of a yellow color. And there's surface mount ones that no one can tell the difference without looking at the code, but little, this tiny capacitor. So what is a capacitor? And what's capacitance? So capacitance is the ability of any device, any component, to store energy in the form of an electric field. So if you were to take that little thing, that little capacitor we drew here, that barrel, and we were to kind of open it up, what you kind of really have at the end of the day, capacitor is nothing more than two metal plates, wire, and another plate of wire coming out of it, that's separated by something called a dielectrics, an insulator, something that doesn't want to conduct electricity. It can be just there are air capacitors where, especially in ham radios, especially older ones, you see these just giant pieces of metal that they kind of rotate close to each other, and but more likely, again, you're using those tiny little ones because we're embedded people. We're not doing big things. Probably the most people that deal with as a homeowner, you may deal with the capacitor, your start capacitor in your compressor unit outside of your air conditioning. But typically, capacitors that we deal with as embedded are very small values. So let's talk about what kind of values those are. So the resistance of the value of capacitance is measured in farad. It's named after Michael Faraday. Typically, we're only dealing with microfarads, nanofarads, very, very small amounts of capacitance. So what's happening? What does this thing do? So what you need to understand is you take a battery, and if I connect one end to one side of it, or one plate of the capacitor, and the other plate to another end, I'm going to get a bunch of positive charge on the one plate and a lot of negative charge on the other. And because even though they're separated, there's an attraction, that field, that electrostatic field, is storage of energy. That's so that the field the field, the connection between the positive and the negative, there's attraction they want to be able to touch, but they can't, induces that field, and that's where the energy is stored. So that's great. What use of that is capacitance then for us as, small voltage, low voltage kind of folks? Before I answer that question, let me just really quick also point out that there is no such thing as an ideal capacitor. So we talked about the fact that we had those two plates. And let's see here. Ideally, the positive charge stays on one, the negative charge stays on the other. Therefore, there's no current flow. There's only just a voltage across. That's not reality. So the reality is you have the capacitor. Oh, I should probably do that first. Let's do the symbol of what a capacitor is. So you'll see capacitors drawn like this. The two plates, and they're separated. Sometimes you'll see it as a line with a little semicircle with a little positive. Some capacitors, especially again the ones that probably have the plus sign, are polarized. That means they can only be hooked into the circuit one way, that there's a positive lead and there's a negative lead. And if you swap that around, more than likely your circuit won't work as you intended. And then there's non-polarized capacitors that don't matter. So a lot of times your electrolytics, the big blue caps guys, those are your polarized, little ceramic, little orange, yellow disc looking things are non-polarized. There's also, there's a whole, just like there's a different manufacturing techniques for resistors, there's different manufacturing techniques for capacitors, but we'll save that for another day. But different capacitors have different characteristics that may or may not be advantageous for your circuit. So like I said a second here ago, it's all well and good. We want to, we love to live in a world where we think that the capacitor is ideally those two plates separated. Like that. Draw that a little bit darker. But that's not reality. So the reality is there is a leakage current. There is some very, very small amount of current does flow through the dielectric and goes from the one lead to the other. Very small, but it does exist. And again, that's a we call it leakage current. There's also what's called the equivalent series resistance. So ideally, there would be no loss into the capacitor, but some of the voltage does get burned up. There's a little voltage drop. So there is some resistance. And there is actually also, and we haven't talked about this part yet, it's coming up tonight, the inductance. There is equivalent series inductance as well. You'll see that sometimes as, so you have this sometimes as ESR. This is ESL. And this is just sometimes R leak. So that's what, if you were to go into SPICE or some modeling program of electronic components, That's how you would actually model a capacitor, because there is no such thing as the ideal capacitor, just two plates separated by a dielectric with no leakage. So again, the purpose of these couple, especially these first few introduction videos, is not to go into great depth of the physics or even some of the deeper usage of it. We just want to basically, when you get your first kit of components, or you crack open your first, maybe your computer dies and you crack it open just to see what's inside. Just want to give you an appreciation of what you're seeing and kind of what are the various parts that you're looking at, and maybe have some appreciation of what it is that they're doing. How are they interacting with each other? Just going down my notes here to make sure I touch everything I want to do. Boom, 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 boom. Yeah. Okay, so what do we use capacitors for when we're doing microcontroller kind of work? Well, most often what we're going to do is we say we have a digital IC chip. And one of those chips is your VCC, or the power. Another pin is your ground. And then you have your signal, all the different inputs, and then your outputs. Most common thing that you'll see, especially around chips, is to use a capacitor across the ground in VCC. So you'd have, somewhere down here, you'd have your plus 5 volts feeds into your VCC. Now you could take that capacitor out, circuit would work just fine, unless other components around it cause the voltage line to drop just enough that your chip kind of goes, wait a second, I think I'm being turned off. And they can obviously mess with your, especially digital logic, anything that goes downstream. So you put these little, call them spike suppression capacitors. And what they do is they charge up, they're usually small, microfarad, maybe a little less, a little more, depending on, again, surrounding circuits, that it stores just enough charge that if there is a drop on the line, instead of having that spike come into your chip, so say I hear your signal drops, just a real quick little, spike, your capacitor there just filters it out. So the chip, after this point, still sees a constant, doesn't see that drop. That's what most capacitors you're going to be using, my opinion, and what you'll see. So little, just again, we call it spike removal, basically preventing a little brownout from affecting the rest of your circuit. Let's see here. Let's keep going down the show notes here. Boom, 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 boom. Let's see here. DC coupling. That's another use of capacitors. What the heck is DC coupling? I'm going to give you a sneak preview of something way in the future that we'll talk about, but we'll do a little transistor here. Now, you don't have to really know much about it at this point, but just know that transistors, say we're working with we want to amplify our voice, an audio signal that alternates. the transistor has to be what's called biased. That means it's got to be given enough DC voltage to kind of turn it on. The problem is, say, like again, in an amplifier circuit, you may have many stages of amplification. All these, and this would be the input, and then say we would tap off here to measure our output voltage. We gotta get our signal in. Well, you could just, you know, say we have like our microphone. Just take that signal and put it right in. The problem is the DC voltage that we're using to bias this transistor to kind of turn it on will want to flow back into circuits that have come before it. So what we do, we take another capacitor, and now we have our audio signal coming in, comes through, and we'll talk about, we just said, you know, wait, you told me current doesn't flow. Well, it doesn't flow through the capacitor. It's a property of AC signals, and as they kind of oscillate back in the circuit. Long story short, think of capacitors, though, as they can act like a short to alternating current or high frequency signals, but they do let AC signals pass through them, sort of. But the nice thing is they also block DC. So the current, the DC biasing current, can't go back. The alternating current, the high frequency current of our audio signal, can pass through and get amplified and handled out. That's probably, DC coupling is probably the second most use. And it doesn't have to be audio. I mean, it can be any sort of analog signal that comes in that we want to amplify before we get to our micro. Any amplification network, you'll have these DC coupling capacitors. So I guess real quick before we go on some other uses, I should talk about there's a property of components like inductors and capacitors called reactants. And you kind of think it as frequency dependent resistance. So resistance is frequency agnostic, regardless of I put a DC signal or if I put a 500 megahertz signal. The resistance part of any device, of the wire of your resistors, it's the same. Reactance, on the other hand, is a frequency dependent sort of resistance. And in capacitors, we call that X sub C. So reactance is given X to show that it's capacitive reactance. We put the lower C down there. Obviously, there's inductive reactance, and we'll talk about that. And that would be an L. So what is the value? What is the resistance or reactance formula? It is 1 over 2 pi FC. So 2 pi F takes the frequency component. The F is the frequency of your signal. C is the value of your capacitor in capacitance in farads, or more likely millifarads or microfarads. So if you think about it, what happens if, well, and we're looking at just F here, the frequency. If F goes to 0, is this number gets really, really small. So, and in the case of frequency, frequency of 0, if it doesn't alternate back and forth, that's DC. So this number gets really, really small as it goes, as it approaches 0. 1 over a really, obviously if it's over 0, math. But as it approaches 0, so it gets really, really small. X of C equals what? Infinity. 1 over 0 can't, again, without going through a math calculus class. In short, the reactance, and the reality is it can't get to infinite, but for the purposes of just proving in your mind what's happening here, as we get to DC, reactance gets really big. Again, so that's why it's blocking DC, can block the DC current from coming back from our DC coupling circuit. Alternatively, what happens when, say, the frequency itself gets really big? Say what happens if it's, some really huge number that you wouldn't really have. Let's say it's like 10 gigahertz. Kind of just huge, a really big number. Well, 1 over a really, 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 really big number, you could even think of it 1 over infinity, is for all intents and purposes 0. If you win the lottery and you're one winner, but there was 10 trillion other winners of a $50 million lottery, you're not going to get your shares, not that much. So when the frequency goes the opposite way, when it gets to be really big, 0 reactance becomes 0. So again, for AC signals, alternating current signals with a significant enough frequency, pass through the inductor. Or at least you can, in your mind, you can conceptualize it that way. And that's kind of, I wanted to throw that in there because of the whole, we just had the discussion of the blocking capacitor. So that's the math kind of behind it at a 50,000 foot level view. What are some other uses? You can put capacitors on the outside of that transistor. You're decoupling this section from the next one, so you'd have both. Again, you'd have a capacitor on the input and the output. Let's see here. We talked about noise suppression. Oh, filters. So sometimes you want to filter out anything above or below a certain frequency. So this is the simplest thing. They call this is single pole, single zero. I'm not in a double E kind of guy, but this is your input and this is your output. Again, what happens if I put it in a really high frequency? So if my F, let me erase this and make it a little bit easier to read. So frequency, what happens to V out? So if I put in just a huge, massive, really, really, really high frequency signal, again, resistor doesn't care about frequency, but my inductor, my capacitor here does. So what happens, again, we said that a capacitor at high frequency kind of acts like a short circuit. It's all going to dump into ground. So the output, I'm going to have is 0 volts. So what this kind of filter is would be considered a low pass filter. So low frequencies and this is the frequency on this axis, and this is my voltage out on this axis, and the Y. So when the frequency is really high of my signal, it gets dumped into ground, and therefore it's a low pass filter. If, on the other hand, I go to, as my frequency approaches 0, again, signal comes in, but now, again, there's leakage currents and whatnot, but for the most part, this now becomes an open, really high resistance, so my signal will just go straight to the output. So my V out in this case tends to equal about my V in. Or another way to look at it is at these really low frequencies, I'm having a high, or did I draw that backwards? Let me think. V in is real low frequency comes out. So low frequency, I'm passing it. High frequency dumps to ground. Yeah, that's right. Low pass filter. If I switch the capacitor and the resistors, that's what I was confusing in my head. I got to switch the position of the capacitors and the resistor. If I put the capacitor up here, put the resistor right here, now I'll get the opposite. I'll get a high pass filter. Again, there's frequency. So this, again, for our purposes, let's think it through. High frequency, very high frequency signal comes in. Now there's a resistance here. I'd rather go to a path of least resistance, so I'm going to dump to the output. A low frequency, I'm going to come in. Well, I can't get through a capacitor because at low frequencies, arbitrarily low frequencies, I act as an open. So therefore, low frequencies, I have 0 volts on the output, and on the input at high frequencies is V in. So my higher frequencies, I'm low, 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 and then I start at higher frequencies. So low pass, high pass filters. There's also ways you can combine these to make band pass filters. You can do band stop filters. So if I only want to let a certain bandwidth proceed through my circuit, if I want to stop only a certain band, we'll get into those more. We talked about, again, motor starts for like in your air conditioning and your compressor unit outside to get your fan started up. Capacitors are there to store up enough charge to help provide enough instantaneous current to get that motor started. And I'll save, obviously it's also for tuning circuits for like radios, but we need to talk about inductors to bring those together. So with that, let's jump over to inductors. Oh, did I just break it? All right, so let's erase all this away. So that's capacitors. Let's talk about inductors. All right. And bear with me. We're still kind of in beta, so I'm still figuring out how to teach this kind of stuff. So inductors, their value is henries. Again, embedded folks, we're not dealing with huge amounts of inductance. So if you ever deal with even dealing with a straight inductor is rare. We definitely do not use inductors by themselves as much as we do capacitors by a long shot. Usually the inductors that we do use are going to be a part of, say, a stepper motor or some sort of solenoid or a relay. We're never just going to really have an inductor except for choking out, like RF noise. But anyway, so Henry's is the unit of measure. L is usually the letter assigned to in different frequencies or different equations when it asks for inductance. L will be the letter given, just like capacitance, in capacitance it was X sub C for reactance of a capacitor. Well, in inductors, it's for reactance, it's X sub L. So what, at the end of the day, the capacitor is a real easy thing to do, or excuse me, the inductor is a real easy thing to do. You simply take a piece of wire and you wrap it around itself into a coil. So you just take a wire and you wrap it up into a coil. Usually the symbols for it is something like that. And there's also going to be another symbol. If we have it, say it has like an iron core, we'll put some sort of symbol to show that there's some sort of ferrous. Usually it's a ferrous, an iron core to help concentrate the magnetic field that's induced, and we'll get to that in a minute. Or again, if it's an air wound capacitor or an inductor, it won't have the little two little lines above it. So again, like I said, we don't use inductors nearly as much as we do capacitors. When we do use inductors, it's because we're using a motor, a relay, a solenoid, as part of a piece of equipment that we're buying, or a component that we're buying. We don't wire our own, so to speak. So, but they are useful for, again, so a solenoid. What is a solenoid? A solenoid is nothing more than, they call it also a sucking magnet. It's an electromagnet. So when you put a voltage across the coil, what happens is a magnetic field is induced. And so whereas the capacitor was storing its energy in form of an electrostatic field between the two plates, an inductor stores energy in an electromagnetic field across the coils. Just like we talked about, there's no such thing as an ideal capacitor. Well, there's no such thing as an ideal inductor either. In fact, kind of the circuit, or the equivalent, or the reality, how it really structured the circuit structure or the component structure of an inductor is some series resistance. Then there's the actual inductance itself. Then there is a parasitic capacitance. And then there is a parasitic resistance as well. So the equivalent series resistance, a parasitic resistance, parasitic capacitance. And what we're talking about, the parasitic, is if you can imagine, you have these coils, and they're, to the eye, they're very tightly wound. But to say if they're insulated, it's insulated wire. What you really have between each coil is there's little capacitors between all these little coils. And that's where, again, reality, the physics versus what we would like to see of just an ideal world. So that's what, again, it would really look like. The thing that people probably would see most on their boards are these little toroids, like little donut shapes. And then there's a wire that kind of wraps all the way around. So these, we call them chokes. So basically, just like the opposite of inductance or capacitance. So whereas x of c was 1 over 2 pi fc, well, x of l, x sub l, is 2 pi fl. So again, if you think about it, what happens when f, the frequency, goes to 0? And what happens when it goes to an arbitrarily high frequency? What is my x sub l? Well, if x sub l is equals 2 pi fl, if I put in 0 there, this all cancels out, goes to 0. So at really low frequencies, there's hardly any reactance. In fact, in DC, once this current reaches steady state, it's like a short circuit. It just goes through, as though, again, there's the parasitic capacitance and there's the parasitic resistance. But for the most part, you can consider it, it's now just a short circuit once the current gets to steady state. Conversely, when the frequency goes really high, what happens into the equation? Well, this goes to infinity. Well, these other numbers, these other 2 pi and the L, doesn't really matter what they are. If I'm already going to infinity with this thing, they all multiply together. For all intents and purposes, I'm going to infinity. In other words, my reactance is going to get really big for high frequency signals. So again, just like the capacitor passes the high frequency signals and it blocks low frequency signals, or DC, the opposite is true for an inductor. An inductor, once it reaches steady state, is a short circuit to DC, and it acts like an open, really high resistance for high frequency signals. That's the kind of the science behind it. What's the real practical use and applications? So in reality, again, like I said, you don't, aside from that little DC, the little choke I wrote right there, to filter out RF noise, you're not going to just use an inductor. You're going to buy a motor. And we will save the math behind how the motor works, but you just realize that there are coils and there are magnets, and because the coils, when the currents pass through, induces a magnetic field, that magnetic field interacts with the magnets themselves, and depending on how you put them all together and the way that they're put together and packaged, and those two fields interact and they create spin, and then you get a motor. Or vice versa, if I have, say, let's see, if I take that motor, instead of making it a motor, so basically taking electricity and generating a mechanical motion, if I have some source of mechanical kinetic energy and I run it across my coil of wires, or make it somehow that the coil wires want to move through the magnetic field of the standing magnets, then I can induce an electricity. I can then induce an electrical current, and that's where things like electrical generators come from. Kind of just the motor working backwards. Take physical mechanical motion, cause a coil to spin, and again interacts with the magnetic field, and I now induce a current across the wires. So motors are what people are going to usually use for stepper motors, little servos. The other potential use is in relays. So let's see here, you'll have think, like a normally open connection, normally closed connection, depending on the little read relays. So what really happens, let me just draw what really happens. So you'll have your source run through the coil. You'll have your relay. It'll have some other signal over here. It's kind of like a switch. So when the current flows through, it creates a field, it tracks these two leads, and now you can have completed some circuit over here. So say this is a little, maybe 5 volts, and this is 12 volts. Now you can use a smaller current, smaller voltage to control a much bigger current. So relays, and what else do we have? Oh, solenoids. So solenoid is a sucking magnet. You just have the coil, and a lot of times it'll be built something like this. You'll have like a little pipe that comes out. And when I put a voltage across this guy, the magnet will get sucked in. When I disconnect the current, pops out. And so you can imagine, locking mechanisms for your door. Maybe you'll use a solenoid to create a lock. A lot of times, though, the thing to think about with inductors, especially these kind of things, is they need a lot of current. So you'll probably need an external power supply. You can't just drive it straight with your Arduino. Same thing with your motors, or else you'll fry them. So one thing, anytime you're dealing with motors, solenoids, before you just jump in and connect it right to your Arduino, think about you probably will need an external power supply. There are some, I've seen some solenoids that can work directly to an Arduino. They're very small. You're not going to, you can't use them for like a lock that protects the door because they're so tiny that you can just physically rip the door open anyway. But they're there. They're possible depending on your use case. And I think that's it. I think that's inductors and capacitors and what I need to talk about from at least getting started with microcontroller kind of level projects. So anyway, that's it. Yeah, I think I've been going way too long. I think my daughter is, hopefully she's asleep by now. If not, go see. Anyway, so send me your comments in the show notes. I'm going to clean up if you're listening on the audio, you're probably hearing a much better cleaned up version. If you're looking at the YouTube video, I apologize. I'm recording it with Hangouts, and it was a little painful tonight. Still working out. I've been trying. So I had the board here underneath the camera. I've had it back here now on the easel. I don't like quite the way the camera hits it with the light. So we're still working. Still a work in progress podcast. Hopefully after 10 episodes or so, I'll have a good feel of how this actually should work and what people really expect. With that, if you've got any comments, head over to steampowerpodcast.com. There's links to everything. We still don't have because I don't know if this podcast will keep it or not. So I don't want to invest in buying up the URL at this time. But if it does catch on, maybe we'll have own standalone website as well. With that, comments I need back, tutorials, project reviews, product reviews, project how-tos, reviewing a project, showing a project from start to finish. We're just doing more, again, kind of classroom theory stuff. What would you prefer to see in a podcast, or get rid of the whole educational thing and just do strictly interviews? Reach out to people that are building cool projects, that are building tools, and interviewing them. Kind of like we did with the last Steam Power podcast, where we interviewed my buddy who is a professor at Full Sail University, which you should check out. That interview was really good last week, almost 2 weeks ago now, for Steam Power. And with that, I will, let me see here, go ahead and shut her down. Appreciate the comments, appreciate your patience, and until next time, what will we do next time? I don't know. Maybe something with transistors. Maybe we'll do transistors next. With that, thank you all very much for listening, and until next time, stay quirky.